Okay, the next thing I want to briefly talk about is just the there's this principle that underlies all this stuff that we're talking about. So when we talk about energy, if we're modeling a ball dropping, we say that its gravitational energy is transformed into kinetic energy. Okay, and we're pretty familiar with this. It's very predictable. We can say approximately how fast it's going to be going. We can talk about energy being lost to thermal energy. But at the end of the day, while this is a really great way of modeling the situation, it doesn't tell us why the ball falls. It doesn't tell us why gravitational potential energy transforms to kinetic energy. It doesn't tell us why a downward force causes something to fall downward. Okay? And so there's a really important concept that underlies all of this and is really responsible for essentially the way the world works. And all of the scientific things that we discuss and learn about all come down to this one kind of foundational, fundamental principle of the world. And the principle is this, that things want to go to the most uniform is the wrong word here, the most disordered energy states possible. Now, what that means is this, okay? If you have a ball up here, it's got lots of potential energy, okay, if it's above the ground. But everything down here on the ground has no potential energy, okay? And what this system wants, what the Earth wants to do, is to take this ball and make its energy level the same as everything else. So the energy is kind of evenly distributed. Okay, and that's kind of the goal of all systems. They all want to go to that point. And so what happens is, when you have something with potential energy, when it gets a chance, it's going to try to transfer that energy into kinetic energy. Now, sometimes there's an object in the way. So if it's sitting on like a platform or a table, it's not allowed to transfer that energy into kinetic energy, so it doesn't. It stays there. It's at a point where its energy level is the same of the things around it. But as soon as it gets the chance, it's going to try to go to this lower energy level. Okay, and there's lots of ways that people describe this. They call it disorder. Okay, the universe prefers disorder, and the way it describes disorder is things being at the same energy level. It's confusing in the sense that if everything's at the same energy level, that would seem like everything is about the same. Okay, when in reality, think about it like this. If you're in your bedroom and you want to put your clothes away, is it easier to take a shirt and fold it or put it on a hanger, or is it easy just to throw the shirt on the ground? It's much easier just to throw the shirt on the ground, but that's much more disorganized. But it's a situation in which you have a lower energy level, okay? And so the measurement of the organization of the universe is called entropy. And as things get more disorganized, the entropy increases. And so the law of the universe is that entropy always has to be increasing. Okay, and we see that when energy is transformed into thermal energy. That's one of the most relevant ways for us, when you lose energy to thermal energy. So an example of entropy increasing is if you drop a ball and that ball bounces lower and lower and lower because its energy is being lost to thermal energy. That means the entropy of the universe is increasing. Okay? And so some people will even use this as an argument for why time travel is impossible, because it would be impossible to go backwards and make the entropy of the system decrease. That's against the laws of the universe. Okay? And so this is about as deep as we're going to get into entropy, but you can do a lot of pretty advanced calculations with it The only thing that we are going to really mention is efficiency. So we've done efficiency before a little bit. So let's go back into efficiency. Efficiency is the percent of the energy that's retained. And so the way we find it is we take the energy out divided by the energy in, and then multiply it by 100 to make it a percent. Okay? So a system that's 100% efficient would have the same amount of energy out as that's going in. Okay? But the second law tells us that's impossible, because for energy to transfer, for something to happen, the entropy of the universe has to increase, which means that energy out has to be less than that energy in, meaning that energy is gone to, say, thermal energy. Okay? And so we're always going to have efficiencies less than 100 because entropy is always going to be there, right? We're always going to have friction interfering with what we're trying to do. And so this is really the only calculation we're going to be doing as it involves entropy. But I want you to kind of think more about entropy and what it means. And I like to talk about it just briefly because this is really what's governing all these systems that we're talking about. This is why this goes to that. This is kind of the reason behind it, the driving force for all these things. And just to wrap things up, this discussion of entropy falls under what's called the second law of thermodynamics. Okay? And the second law is that for a reaction to take place, or for something to happen, for an interaction to happen, the entropy of the universe must increase.